Bismillahirrahmanirrahim. I welcome you to the 6th lecture of the series of lectures on advanced computer architecture. In fact, today's discussion is a concluding discussion on the instruction set, principles, and architecture. Last time, we talked about the essential elements of computer instruction world, where we discussed what are different types of operands, where these operands can be obtained as the source operands, and where the result after the execution of the instruction is to be placed. Also, an instruction set gives us an information about where from the next instruction is to be obtained. Then we talked about different parameters of the instruction word, such as the length of instruction word. And in this discussion, I gave you 3 different ways of writing an instruction word. The instruction word can be written as a variable length instruction word, a fixed length instruction word, and a hybrid length instruction word. As the name indicates, the variable length instruction words format is 1, where an instruction word, length of the instruction word, varies depending upon the type of instruction. The fixed length instruction words are those where the length of the instruction word always remains constant. For example, the instruction word of the MIPS architecture, which is in our discussion, we are considering 32-bit instruction word. Whereas a hybrid instruction word is the most commonly used and most efficient method of writing an instruction word, which is having variable lengths, but for one particular mode of operation, the length is fixed. So this is why it is called a hybrid instruction word. Then we talked about the categories of instruction word. That is how we can write an instruction word addressing. An instruction word can be written as a zero address instruction word, such as the instructions written for the stack machine. Then one address instruction word, such as the instructions written for the accumulator based machines. The 2 address instruction words, where one of the address is used initially as an address of the source operand, and after the execution of an instruction, it is used as a destination address. The 3 address instruction word is one where the addresses of 2 source operands and the address of destination location is given, are specified in the instruction word. And the 4th address instruction word is one where we define the source addresses, 2 source addresses of the 2 operands, the destination address, and the address of the next instruction. Then we talked about I gave you the comparison of the hybrid instruction words, where we discussed that what are, in fact, the advantages and disadvantages of using different types of instruction words, such as we said that minimum number of memory bytes are required for 1 byte instruction word, and maximum number of memory bytes are required for 4 byte instruction word. Then we talked about the MIPS instruction word format for the RISC and the MIPS architecture, which is a fixed length instruction word. The MIPS architecture is a 32-bit instruction word architecture, which supports 8-bit, 16-bit, and 32-bit operands. It has got three distinct types of instructions which can be defined with the help of this type of instruction word. And these three distinct types are the immediate or I-type instruction. The I-type instruction is one where one of the operand is defined as an immediate operand. The second type of instruction is known as the R-type instructions, or the register type instructions, where both the source operands are placed in a register, in two registers, and the result is also placed in one register. So in this case, all the three addresses are the register addresses. The third type of instructions are known as J-type instructions or jump type instructions, where this type of instructions are used to specify either simple jump, conditional jump, or procedure call or control operations. Then we also talked about what are different types of instructions which can be used, and these are which are supported by the MIPS architecture. And these instructions are the arithmetic and logical instructions, the data transfer instructions, and the control flow instructions. Then, after this much discussion about the basics of the instruction set architecture, we discussed in details the format of these instruction words, and then how we can represent these instructions and the meanings of these instructions by using the register transfer language. The digital signal processing deals with continuous data streams, whereas the media applications involve two-dimensional and three-dimensional images. Therefore, some new architectures have been introduced to support the addressing modes, new data types, and operands for both the signal processing and media applications. The digital signal processor, which deals with continuous data stream, rely on circular buffers where the data are added to a circular buffer and a pointer is used to identify the start and end of the buffer. If it is pointing to the end of the buffer, it is set to the start of the buffer. Otherwise, the pointer is incremented to the next address. All recent DSPs use modulo or circular addressing modes to handle continuous data streams automatically. Here, every address register keeps a start register and an end register, and it allows auto increment and auto decrement addressing modes to reset when they reach the end of the buffer. The new addressing modes are included in the instruction set architecture for digital signal processing to handle applications such as fast Fourier transform or similar applications. We know that the fast Fourier transform starts or ends its processing with the data shuffled in a particular order. For example, the fast Fourier transform for 3-bit data, which has got 8 items in radix 2, it can be represented as shown below. Here you can note that the first value, that is 0, which is represented as 000 in radix 2, it is transformed to the same value. You can note that this transformation is simply the reverse of the initial addresses in radix 2. For example, if we consider the second line where the original value is 1, which is having a binary equivalent value equal to 001, it is transformed to a decimal equivalent value equal to 4, having the binary equivalent value equal to 100. So this shows that the value of 1 has been reversed in binary. That is, the least significant bit becomes the most significant bit, and so on. Similarly, you can see that the value of 5 for FFT has been reversed, but it is having an equivalent binary value because the reverse order of 101 is the same as the original order of the value 5 in binary. Here you can note that we can find the fast Fourier transform by using another simple addressing mode. This simple addressing mode is usually known as the bit reverse addressing mode. The bit reverse addressing mode basically reverses the order of the bits of the address to find the address of the transform. Here, some hardware may also be used to the lower order bits of the address and the number of bits which are to be reversed. That can be determined by taking into consideration the steps involved in the fast Fourier transform algorithm. Now, with this much discussion on the addressing mode for the digital signal processing, let us talk about the operands for the media and signal processing. The media applications deal with the 2-dimensional and 3-dimensional images, where a 3-dimensional data type can be defined with the help of 4 basic components. These components are usually denoted as the x-coordinate, the y-coordinate, z-coordinate, and w-coordinate. This 3D data type is also referred to as a vertex, where the vertex value for the graphic signals is usually represented by 32-bit floating point value. The formation of a pixel for 3-dimensional images is shown here, where you can see that the X, Y, and Z vertices specify a graphic primitive that is a red, green, and blue value. This value is in fact representing the 3 vertices of a triangle. However, the 4th value, that is W, it helps with the color and to identify whether it is a hidden surface or it is a transparent surface. A triangle is visible when it is depicted as filled with pixels, as it is shown over here. The pixels are typically represented as 32 bits consisting of 4 8-bit channels. These channels are identified as the red, green, or blue and represented by R, G, B. Whereas the 4th component is represented as A, which gives us the transparency of the surface or transparency of the pixel when it is depicted. Let us discuss this with the help of an example over here, where we can assume that we have a pixel which is stored in an image array of 24-bit picture element. Here we are considering 24 bits instead of 32 bits because for this example we are not considering the transparency section. The pixel value can be represented with the help of 3-bit unsigned integers as shown over here. Here the RGB value of E5, F1, D7 hexadecimal, which is representing the values of red, green, and blue. Here the value of red is equal to E5 hexadecimal, green is F1 hexadecimal, and blue is D7 hexadecimal. Here please note that the RGB values show the brightness of the pixels. The higher is the value, the brighter is the pixel. Now, in order to explain this, let us consider 2 example pixels, that is, the pixels represented by the value E5, F1, D7, and the second pixel AA, C4, DE. Here, as the value E5, F1, D7 is greater than the value AA, C4, DE, therefore the first pixel is brighter as compared to the second pixel. However, we can change the brightness of the pixel while doing some image processing by either adding some colors to each component of the color or sometime reducing the color from each component of the color. However, at the digital signal processor, the addition of the colors is performed by using unsigned arithmetic operations, and while performing this arithmetic operation, we ignore the overflow. For example, let us consider the 2 pixels which we considered earlier, that is the pixels with the value E5, F1, D7 and the pixel with the value AA, C4, DE, and add a value 20 hex into each color and find out its effect on the brightness. You can see from this arithmetic operation that we are now adding a value 20 hex to each color, that is to E5. When we add a value 20, it results in a value 05 with 1 overflow. However, as we have mentioned earlier, we have to ignore the overflow. Therefore, the value resulted in this addition is equal to 05. Similarly, we add 20 to F1 and it results in a value equal to 11. Again, over here, we ignore the overflow. And to the value D7, we add 20 and it results in F7 without any overflow. Similar operation performed on the other pixel, that is AA, C4, DE, it results in CA, E4, FE. Here you can note that the pixel E5, F1, D7 loses its brightness because when we add these colors, it results in a value which is very, very small as compared to the original value. The original value was E5, F1, D7, whereas the resulting value is 05, 11, F7. This shows that the red and green brightness are now much less than the blue brightness. However, the pixel CA, E4, FE, which is the result of adding color to AA, C4, DE, is now brighter than its original color. Multimedia processing systems, which are given in this table. You can see it from this table, where you can see that over here a very little common features are there across all these 5 architectures, which are shown here in this table. All these architectures are fixed with operations, which are performing multiple narrow operations on either 64-bit or 128-bit ALU. However, you can note it from here that a narrow operations are shown as of type B, which are performed onto byte, of type H, which are performed onto half word, of type W, which are performed onto a word long data, and of type 8B, which is performed onto 64-bit or double word data. Now we will be talking about digital signal processing issues. As you can see from this table, the most important digital signal processing issues are the saturating addition and subtraction, result rounding, and multiply accumulate. From saturating addition and subtracting, we mean that when the result is too long, how to handle the overflow. Result rounding means that what is the technique which is to be used for rounding of results. In fact, there are a number of algorithms available for rounding off the result. These algorithms are known as IEEE standard 754 mode algorithms. And the last issue, that is the multiply accumulate, it deals with the vector and matrix dot product operations. Now let me talk about these issues one by one in detail. The saturating add subtract is one which is very, very important, because DSP results cannot ignore the overflow conditions. Because if it ignores the overflow conditions, then there are chances that we may miss certain events which are to be taken care of. Therefore, special care is to be taken to handle the results with overflow. And for this type of operations, the saturating add subtract instructions are available in the instruction set for the DSP operations. The next is the result rounding. The result rounding, as I just mentioned, it deals with whenever we are using the DSP operations. In DSP operations, wider accumulator is to be used for narrow ones, for narrow data. So this means that we have to take care of where the result is to be rounded off and how to deal with the overflow. Whereas the third and the last issue of the digital signal processing is the multiply accumulate. This is known as MAC or MAC. The MAC operations which are available in the DSP instruction set are the key to the dot product operations onto the matrix and the vector data. So the vector and matrix multiplication, it requires accumulated multiplication, and for this purpose special instructions are available in the instruction set of the digital signal processing architecture. So with this much discussion about these advanced type of instruction set architecture, in fact, we have talked about almost all aspects of the instruction set architecture, which is used for simple computer up to the complex architectures such as needed for digital signal processing or multimedia applications. Now I will switch on my attention to discuss the parameters, to discuss the instruction set architecture performance attributes, and to see how the instruction set architecture performance can be measured and then optimized. While talking about the instruction set performance, the role of compiler is very, very important. As you all know that compiler is a program which facilitates the interaction between the high-level language and the machine, and therefore it converts the high-level language program instructions into the assembly language of a particular instruction set architecture. While talking about the performance of an instruction set architecture, first of all, let us see what, in fact, measures the instruction set architecture performance and how it is being classified. And instruction set optimization can be classified. The performance of an instruction set can be classified into different factors, such as the high-level optimization. The high-level optimization is often done on the source with the output fed to the later optimization stages of the compiler. As you are familiar with the compiler usually translates the high-level instructions to the assembly language or to the machine language level by passing through different passes. These passes may be, there are compilers available corresponding to 4 passes or 2 passes. So, high-level optimization is done at a level when the source is available and this source is to be fed into some later optimization section. The second level of optimization is known as the local optimization. The local optimization is done with a single line code or a block. This actually means that if we are to compile a loop or a block, then the block compilation is to be optimized at its own level. So this is why this level of optimization is known as the local level optimization. The third level of optimization is known as the global optimization. The global optimization basically extends the optimization across the branches. That is, when we have to optimize the overall code looking from the top position and spreading along different branches of the system, then in this particular case, we call this type of optimization as the global optimization. The next, I will be talking about the processor-dependent optimization. The processor-dependent optimization is one which deals with the instruction set architecture of a particular class of the processor, and we optimize the code depending upon the instructions available in a particular instruction set. For example, if an instruction set has got an instruction, say, called exchange, and which may be used to exchange the data between 2 registers or 2 memory locations, then if this instruction is not available in the instruction set, then usually a compiler writer needs 3 instructions to perform this operation. But if this instruction is available as a single cycle instruction in an instruction set of the particular processor, then in that case only 1 instruction can be used to optimize the instruction dependent or the processor dependent optimization. The other most important thing which affects the performance of a system is the processor is one which is the register allocation. The register allocation deals with how registers are associated with the operands. I will talk about this in details in a few moments. Now we will be talking about further the impact of compiler technology onto the performance of the instruction set architecture. While talking about the impact of the processor technology, the interaction of compiler and high-level language, it affects how program uses an instruction set architecture. The 2 important questions arises here are how are the variables allocated? Number 2, how are registers needed to allocate variables appropriately? These 2 questions are addressed by using the areas in which high-level language allocates registers. These 3 areas are, number 1, the stack area. The stack area is used for local variables. The stack area basically grows and shrinks dynamically when the registers are, when this stack is being allocated or it is withdrawn. The objects on stack are primarily the scalars, that is single variables rather than arrays. It is very important to note that stack is directly not recommended for arrays. Rather, it is recommended for scalar data. The register allocation is much more effective for stack allocated objects. The second area is the global data area. The global data area is one which is used to allocate statically declared objects such as the variables and constants. These objects are mostly arrays and other aggregate type of data. Register allocation is relatively less effective for global variables as compared to the stack variables. The global variables are alicets. That is, there are multiple ways to address, so make it illegal to put a register over here, because in this particular case what we are saying is that there are multiple ways with the help of which we can allocate these registers. Therefore, it becomes illegal to allocate global data to a register. The third type of data area is known as the heap. Heap is used for dynamic object allocation. The dynamic object allocation is used to allocate objects such that they do not adhere to stack. As we have mentioned earlier, the stacks are used for scalars, whereas the heap is used for the arrays. Hence, the stack do not adhere to the particular, the stack do not adhere to array type of data. Therefore, most heap variables are aliased, so register allocation is almost impossible for the heap. So this means that the heap cannot be allocated to registers. Now, with this much introduction about the data allocations, I will be talking about the floating point operations, which is the last topic in instruction set architecture. So far, we have been talking about simple integer type of instruction set architecture for integer type of instructions. Whereas we have been pointing out from time to time about the floating point operands. The floating point operations are the instructions which manipulate the floating point data. As you can see from this slide, there is different instructions which are written for this. For example, move.s means the transfer of single precision floating point data, and move.d means the transfer of data which is a double precision data. So this type of instructions, they are used how we can handle the double precision or single precision data. The other factor which you can see from this particular information given over here is when we want to get greater performance for graphic routines, MIPS64 offers paired signal instructions. The paired signal instructions are those which are used to perform two 32-bit floating point operations on each half of 64-bit floating point data. These instructions are like add.ps. The add means it is the addition of paired signal instruction or paired single word. Paired single word is one which is which includes two 32-bit data values which are going to be handled by 64-bit ALU as pair of two 32-bit values. Similarly, SUB or subtract.ps or MUL means multiply.ps or div means divide.ps. So with this much information about all these different types of instruction set, I will now summarize or put together what we have been talking about in the previous two lectures and the today's lecture regarding the instruction set principles. So for this purpose, let us have a look over here. While talking about this, the earliest architectures were limited to the instruction sets by the hardware technology of that time. In 1960, stack architecture became popular because it was viewed as a good match of high-level language. Further developments in 1970, the main concern of the architecture was to reduce the software cost, thus produce high-level architecture such as the VAX machine. In the era of 1980s, the architects returned to simple architecture that took place due to the sophisticated compiler technologies. Then, from 1990 onward, some new architectures were introduced. These architectures looked into the addressing of double word, that means 32-bit or 64-bit size data, optimization of conditional branches via conditional execution. That is, the conditional move. Within one instruction, the condition is tested and then the data is transferred from one register to another register or from one memory location to another memory location. Then at the same time, the optimization of the cache performance via prefetch, that increased the role of memory hierarchy in the performance of computer. So this we will talk about in much more details when we will be talking about the use of cache in the design of computing systems. The other area which people looked into was the facilitation of the multimedia. The multimedia support, the systems were developed such that they are capable of performing support to the multimedias. However, at the same time, particularly with reference to the digital signal processing, the floating point instruction, handling of these such instructions became very important, and new instruction set architectures were introduced for dealing with the faster floating point operations. I have already told you that how we can do this by considering the SIMD structure and so on. So Taking into consideration all these factors, we have in fact discussed different for the instruction set architecture from different point of views. Now, in order to conclude this discussion on the instruction set architecture, I will summarize what we have already talked about the instruction set architecture up till now. We started our discussion with the introduction of three pillars of computer architecture, that is the hardware, software, and instruction set. Then we said the instruction set is basically a mean to provide an interface between the hardware and the software. Then we talked about the taxonomy of the instruction set architecture, where we said we discussed the stack type, the accumulator type, and general purpose register type of architecture. Then we discussed the different types of the operands which are used, such as the integer type, the floating point type, and the character type. And then we talked about the sizes of the data which is used, such as the byte, half word, word, and double word. Then we took into consideration the classification of operations, where the operations can be classified into four distinct sections or four distinct areas, such as the arithmetic and logical instructions, the data transfer instructions, the control instructions, and then some support instructions. Following this, we discussed the different addressing modes, which included the immediate addressing mode, the register addressing mode, the direct or absolute addressing mode, and indirect addressing mode. Then we talked about the classifications of indirect addressing mode in details, including a discussion onto the register type, the index type, the relative type, and memory indirect addressing modes. And then we talked about the special addressing modes, which include the auto increment, auto decrement, and scaled type of operations. The control instructions and their addressing modes were discussed in details, including discussion onto the branch, jump, and procedure call and return operations. Then we switched on our attention to encoding of instructions, where we discussed in the last lecture the essential elements of computer instructions, and then instruction word length, which I summarized in the beginning also, and then the comparison between the different formats of the hybrid word format. Talking all about all these things, then we talked about the MIPS instruction set format, which supports basically 8-bit, 16-bit, 32-bit, and 64-bit operands, and three major types of instructions, such as the J-type instruction, the I-type instruction, and R-type instruction. It also supports the arithmetic and logical instructions, data transfer operations, and the control flow operations. Then, having made all these discussions, today we discussed the multimedia and digital signal processing instructions. We talked about the types of multimedia and digital signal processing operands. What are different types of narrow operations which can be handled as 8-bit, 16-bit, 32-bit, and 8-byte double word type of operations. Then we talked about the saturating problems, the result rounding, and multiply accumulate problems in case of multimedia operations. And then at the end, we talked about the role of the compiler in instruction set architecture. So up to this, we have been talking about in details what is an instruction set architecture. Now at this stage, I would like to tell you that now you please go through the number of examples and problems given in chapter 1 and chapter 2 of your textbook and solve these problems. I will also be providing you number of examples which have been solved in your lecture notes, and these lecture notes will also cover some of the examples which are to be studied by you. Then at the end of each set of these lecture notes, you will be getting different assignments also, which you will be required to submit according to the schedule available. This way, up till this stage, I have summarized or overviewed what is the overall computer architecture, what is the difference between computer architecture and computer organization, and then we discuss the principles of instruction set architectures. So, with this much discussion and introduction about the principles of instruction set, from next time we will switch over to the discussion onto the design of data path, different types of data path designs such as single cycle data path, multiple cycle data path, and then the most important one, which is the pipeline architecture. So we will spend relatively good time in overviewing the pipeline architecture because that form the basics for your next steps, which are instruction level parallelism and so on. So with this much discussion today, I will stop over here and say you Allah Hafiz till next time. Thank you very much.